with limits with graphs, as you can see here. The limit of a function is the value as x approaches a certain number, okay? This is your notation for it that you see up here. It's abbreviated LIM, okay? This tells you what x is approaching. X is approaching c. It'll tell you a number there typically. F of x is just going to be whatever function you're talking about. A lot of the graph ones will just say f of x because they're not real worried about the equation. They want you to get it from the graph. Some of the other ones that we plug in will actually have a function there, something with an x in it. So what we do when we use graphs is that we literally follow the graph towards that certain x value that they're telling us, and we see what it's getting closer and closer and closer to. Some of these are going to be kind of duh questions because you're going to be like, what's so hard about this? And then others of them you'll start to see how the limit can be different than the value of the function at that point. So for example, to start with an easy one here, this first one to the left, where you're doing the limit as x approaches 1, okay? So that literally means on my graph here, here's my x is 1. I'm looking as I come from the left towards 1 and from the right towards 1. And I'm seeing what this value is getting closer and closer and closer to. A limit is a y value. So as I follow those arrows in from the left and to the right, both of them are getting closer and closer and closer to a y value of what? 2. Now, in this case, f of 1, which is just asking you for the function value at 1, happens to be the same thing. Okay, this is a very easy, simple function to start with. We're starting with something easy on purpose where those two match. They will not always match, and we're about to see that in a couple places here. Okay? Second one to the right, just to practice another easier one, I need to find the limit as x is approaching 1 again. We're going to just stick with 1 for a while. So I approach 1 from the left, and I look at where it's getting closer to. We look at your function as we're approaching it from the right and see where it's getting closer to. Both of those are converging to a y value of what? 3. What is the actual function value at 1? Also 3. If those two match, and we're going to talk about this later this chapter, these are called continuous functions. That is a definition of being a continuous function, that the limit, it's getting closer to the same number as it actually equals at that point. Now, we're going to throw some different types at you, which is the next two here. If you look at the bottom ones here, the ones in the middle, I'm still doing the limit as x approaches 1 here. So on this next one, I'm approaching 1 from the left, and I'm approaching 1 from the right. They're both getting closer and closer and closer to a certain number in this case, which is what?
2.
It's getting closer to 2. However, there's a hole there, which means the actual function value at 1, what? There's nothing. And so this is where we use this notation DNE. This stands for does not exist. Okay? You can use DNE. You can use DNE for a limit if a limit doesn't exist, or you can use it for a function value if that doesn't exist. It doesn't exist because there's a hole in the function there.
But why does that limit exist, though?
Because it's still getting closer to 2. It's just literally at that exact point. There is no function value, but they're still getting closer to 2.
The limit's like where it's going.
Yes. The limit is what it's getting closer to, not necessarily what it actually equals. So then we can throw a couple other weird ones. I'm going to go with the one below it before we go to the ones to the right and the over there, because those are a little bit different. The one below it works the same way. If I'm finding the limit as x approaches -2 here, I want to approach the x value of -2 from the left and from the right and see if it's approaching the same number. In this case, those are both converging towards a y value of what? 2. However, because of the hole, what is the actual function value? Does not exist in that case.
Is that anytime there's a hole?
Typically, but not always. Sometimes there will be a closed dot to make up for the open dot. And we'll see that in just a second. Now, we can have a different situation, which are these ones on the right. Okay? This is one where things are flip-flopped for us. If I want to do the limit as x approaches 1 in that top right one, I need to approach 1 from the left, This one is getting closer and closer and closer to a y value of what? 3. If I approach it from the right, getting closer and closer and closer to a y value of what? -1. Those two are not converging to the same thing. This is a case where a limit does not exist. Okay? These are the ones that can get weird. Okay? So, again, that's because the left side is getting closer to one number, the right side is getting closer to a different number. If they don't match, limit doesn't exist. Now, be very careful about this next part. F of 1 is saying, where is this actually defined at 1, which means it's asking me for what? The closed dot. Okay, so this one has an open dot up at the top. We don't worry about that. We worry about the closed dot, which has a y value of -1. This still is not a continuous function, though, because they don't match. Clearly also not continuous because you'd have to pick up your pencil as you drew. Okay? All right, one more like that, and then we'll do some tables and be done. Okay.
So we're looking for on the function the y value that this.
Yes. So if I'm doing the limit as x approaches -2, I'm going to approach -2 from the left here. That one's getting closer to a y value of what? 2. If we then approach it from the right following this, it's getting closer to a y value of -2. So what's true about our limit there? Does not exist. However, the function value at -2, okay, in this case, however, okay, we have an open dot up here. What do we assume if there's not a dot down on the bottom one? We actually assume that's a closed dot there, down there. Okay? All right. So if there is no open dot, you may assume a closed dot there. So our function value at -2 is actually what? -2. All right. Before we flip over and talk tables, any questions about these? No? All right. Some of these are obvious from graphs. Some of them are not obvious from graphs. Okay? All right. Now, tables is a second way to solve these. Okay? The reason we would use a table for this, okay, we have something called, in limits, it's called direct substitution. It basically means plugging the number in itself. You can find a limit by plugging in a number to a function, okay? However, if I took this function that they've given me that they want me to find the limit of, and I plugged in 2 right here, what would happen? I would get 0 on the bottom, which means I can't get an answer from direct substitution. Okay? Direct substitution is just plugging in the number. That's how you always try a limit first. Always. You don't graph it, you don't do a table, you don't do any of that. That's the easiest thing ever. You just plug it in, see if you can get a number back out. That's something like number 3 down here. Okay, number 3 is a good direct substitution if I want to find the limit as x approaches 1. If I can just plug in 1 for x here and get a number back out, don't waste your time doing anything else. That's another way to find a limit. Okay? So that's just going to be 2 times 1 plus 1 or 3. Okay? There's no point in doing a graph, a table, or any of our other methods if you can directly plug it in. However, we learn the tables for things like 1 and 2 because if I plug those in, I don't actually get an answer out of that. Sometimes it might be easier to get an answer from looking at a table than it would be from a graph. This is one that the graph would be a little bit funny. Okay? And this is also where I would start using what I said about using the store button. I wouldn't want to type this a million times. So take a minute on your calculators, maybe split it up at your table, because let's be honest, the skill we're practicing is not plugging in numbers here. It's getting a conclusion from that. So at your table, split it up and plug in those numbers. So right there we were plugging in numbers, yes? Yes. Not very difficult. All right, what we are doing here, what we're looking at here is we're approaching 2 from the left and from the right. Okay? How do I know that? This says x is approaching 2. All of these numbers right here, the first 4, are all numbers slightly less than 2, right? We're getting closer and closer and closer to 2 as we go from the left into this. So we're approaching 2 here in the middle. All of these numbers on the right, okay, these are just a little bit higher than 2, okay? What I guarantee will be the hardest part for some of you in this entire chapter is figuring out what numbers to put in those tables. Like what's actually a little bit higher than 2. Is it 2.0001 or is it 2.1? It's shocking how difficult that is because you're not given these tables most of the time. Okay? So if I'm going to make a conclusion about this, like I did based off the graph on the previous page. If I follow these numbers, I'm going from -10 to -100 to -1,000 to -10,000. If I'm following that pattern, if I kept adding 9s to that 1.99, okay, what would these numbers all be getting closer and closer and closer to? Well, those numbers would be getting closer and closer to 2. The numbers on the bottom that we've been finding, they're going to just keep adding zeros, right? Bigger, 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 negative, which means it's going to where? Negative infinity. Okay, the bigger those numbers get without stopping, they're going closer and closer and closer to negative infinity. If I follow the right side in, 10 to 100 to 1,000 to 10,000, as I kept adding zeros into those 2s, those would keep adding zeros at the end. So those would be going to where?
Infinity.
Okay, now, if one of them's going to negative infinity, the other one's going to positive infinity. What does that tell me about the limit? Opposite. So what does that tell me about my limit?
0.
Does not exist. DNE is always if...
Thank you, Gavin.
Guys, just shush for a couple minutes. DNE means they are going to different numbers. One is going to negative infinity, which is down. One is going to positive infinity, which is up. Therefore, our limit does not exist. Some of them, however, will get closer and closer and closer to the same number in the middle, which is what matters to us. Okay? So we're going to try that with number 2, and then we'll quick direct substitution on the last couple. Okay? So same numbers we're plugging in here. Again, take a minute if you have it on your paper. And again, the plugging in should not be the difficult part, hopefully. As we said before, the x's are getting closer and closer and closer to 2 in the middle. So our goal is to figure out what the y's are getting closer and closer and closer to. So if it goes from 3.9 to 3.99 and it keeps adding 9s on the left, and it goes from 4.1 to 4.01 to 4.0001, what's it getting closer and closer and closer to in the middle? 4. Good. And that is your limit. Okay, so if it gets closer to the same number in the middle, you have a limit. If it's different numbers, you don't.
If it's different, that's why the first one was doesn't.
Yes. All right, last couple here, 4 and 5, then I'm done. On the bottom here, 4, you may use direct substitution where we plug it in as long as you know where to plug it in. Okay? This one says x is greater than or equal to 3. Okay, so if I'm finding the limit as x approaches 3, if this section of the graph is greater than or equal to 3, is that approaching 3 from the right or the left?
That way.
That way.
From the right.
From the right. Okay, this one's coming in from the right because it's greater than or equal to 3, so that's the section off to the right. This one, x is less than 3, is approaching 3 from the left. Okay? If it happens to be that you are finding the limit where that number is here, like this is the number that we're trying to find the limit of, that means I have to plug it into both and see if it's coming to the same place in the middle. Okay? If it was like the limit as x approaches 2, you would just figure out which one of those two categories 2 fit into. So is 2 greater than or equal to 3? Then you plug it in the first equation. Is 2 less than 3? Then you plug it into the second equation. It just happens on this one we're finding the limit where the two pieces come together. So I would have to plug it into both to see. So in this case I would say 2 times 3 minus 4. Let's see what number we get from that. In this case we're going to get what? 2. And then I'm going to do 5 minus 3 for the second one. I'm also going to get 2. If they're approaching the same number on both of them, what does that mean? That's your limit. If it's approaching 2 different numbers, what's true? Limit doesn't exist. You can also, without doing any work at all with a table, figure out if there is a limit or not. They've given you a table here in number 5. You don't even know what your equation is. It doesn't matter. Okay? If you follow the values in towards the middle, these are all going closer and closer and closer to probably, I'd say, 1.1, because they're getting closer to that right there. And then in this one, they're all getting closer to what number? Negative 1.1. What does that mean about my limit? Does not exist. Okay? All right. Because a lot of this stuff is short, and I just want to do a couple things here and there that are a little bit extra before homework. I have a packet that you're going to just hang on to. You're not doing all of it today at your tables. I'm just going to tell you a couple problems to do, and then you'll have homework time. Your homework for this, however, is the next page, front and back, wherever that happens to be in limits of functions. This one. Okay. Yep. Front and back on that. The back is just reading the graphs, so the front part is the work. Okay. So that will be your homework for